Hi guys, Dr. J here, and in this video I'm going to give you just kind of an overview of the whole area of Kriging. Now there are a number of other videos on the Canvas website that you can look at. So in this one I'm going to kind of give you a little bit of the background behind Kriging, very small amount, and then we'll kind of look at Kriging from a big picture viewpoint. So our main goal when we're doing Kriging is, of course, we have some data and we would like to estimate what the value is of our data at some new location where we don't have data yet. So in this example here, so we have some data shown by the dark colored squares. So we have some data, and perhaps at this location here, where we don't have any data, we haven't sampled there, we would like to estimate what the value is going to be based on this existing data that we have. And our overriding assumption here is that values that are located at points close in space are more similar than values far in space, or they tend to be more similar, perhaps I should say. And of course, this idea of closeness in space is going to depend on the spatial correlation characteristics of the observations that we have. So if you have data that are close, what does close mean? It's within some distance scale where data within that kind of range of distances is correlated, and outside that range is not correlated. So it's some type of correlation length scale that we want to know and understand, or that we need to know and understand. And of course, we've talked about how you could get such a correlation length scale through variogram analysis. So oftentimes we use variogram analysis first to try to look and see what are the spatial length scales in our observations. Sometimes they can be anisotropic, be different length scales in different directions. Either way, we would like to know what are the spatial length scales of our observations. How correlated are they in space? And over what distances? And so once we have that spatial correlation length scale defined, we can define what it means to be close. That's within one of those spatial length scales. And far is, of course, farther than that. So that's a very practical way to think about what things are close or far in space. Now, the way that we're going to actually estimate what this point is through Kriging, and this is just basically a weighted average. So our estimated data, denoted with the star there, that's our estimate, is going to be equal to our original data, a weighted average of that original data. So we're taking these lambda weights here, these are weights, and we're just going to take an average of our data where the weights are given by these lambdas. What are those lambdas? Well, we need to solve for what those lambdas should be for this estimation location. And there's a couple of principles here that we're using, that a datum close in geological distance to the unknown should get a large weight. That's basically the comparable statement to our overriding assumption here. If you have data points that are close, that are nearby, and again, close is defined by that correlation length scale, then that data point is going to get a large weight. A point that's farther away from our estimation location here is going to get a smaller weight. And if you have data that are close together, such as these 2 points here, about the same distance to the observation and very close to each other, they are in some sense redundant and should share their weight. So we would perhaps grant weights that are similar for these 3 clusters of data, with this data point having the highest weight, this one having the smallest, and then this pair of data points sharing a weight, which is a little bit less than this one. So each individual data point might be much less, but combined together, their weight would be a little bit less than here, but probably more than this one, if that makes sense. So what Kriging is and is not, it's one method for interpolating, which is essentially predicting values at new locations. It's going to try to give us the best estimate that we can get based on the data that we have. And it uses more information. How is it the best? It uses more information from the data than most other interpolation methods. So if you just do inverse distance, which we'll talk about in a minute, or you just do spline interpolation, we're able to get more information out of the data using a geostatistical approach, because we can, for example, estimate what that correlation length scale is that defines closeness. Now, one type of interpolation algorithm or prediction algorithm, which is very similar to Kriging, is the inverse distance weighting scheme. And so here is the case where you have a point, which I've denoted with the x, and you've got some data. You want to estimate what that point is. A common interpolation scheme that people have used is the inverse distance weighting, where the weights are proportional to, I should have proportional here instead of equals, the weights are proportional to 1 over the distance between the 2 points and then raised to some power p. So p can be 1, so 1 over r, p can be 2, 1 over r squared, and so on and so forth. Now, what does this method give us? It does account for closeness in the data, but one thing that it doesn't do is account for data redundancy. So what if we had, for example, this situation here on the right, where you have one data point over here by itself, and then a bunch of clustered data over here? Well, obviously, you would think that this data should get a weight which is altogether comparable to the weight of this data point over here, and yet we're not able to sort of do that with this inverse distance weighting scheme. So a very commonly used scheme, it does definitely have its place, but it doesn't use as much information from our data as we would like. It doesn't account for this data redundancy here, where you have clustered data points. And so Kriging is going to also use distances, but it's also going to account for this clustered data. It'll account for the type of spatial continuity that we have. So for example, we can have an isotropy in the spatial length scale. Different lengths can be different effective distances in different directions. I'll say an example about this later, and it'll make more sense. And so here is just Kriging equations. We'll talk more about what these mean and how to derive them in just a second. So the idea here is we've got some data, we want to estimate our location, we've got our weights that we need to solve for, and then once we have those weights, we'll calculate just directly taking the weighted average of our data to get our new estimated location. And the idea here is that these weights are going to be related to the data locations, where we're going to take the distance between pairs of points in certain directions. So we'll take both distance and direction to calculate the covariance function between each one of the data points and themselves, so all the data with each other, and then all the data with our new estimated location. So that's these lines here that are connecting our existing data with our new estimate location. And let's formalize this a little bit. So we have here our simple Kriging equations. And in another video, I went through how to derive these, but here's what they work out to be just in practice. So we've got a matrix here, a 3x3 matrix. If we have 3x3 matrix, that means we have 3 data points. So in this case, we have 3 data points. We need a 3x3 matrix, and this term here is the covariance between point 1 and itself. So just data point 1 and data point 1, whatever that variance is. And then we have sigma 1, 2, which is the covariance of data point 1 with data point 2. And this is, of course, where distances between data points comes into play. So we have our matrix of covariances, and this is associated to the data. So this capital sigma here, which sometimes I'll denote with a sigma ij, just to let you all know that it's related to the data. So this sigma is the covariance of the data with itself. It doesn't change based on our estimated location. So it doesn't matter where we want to estimate a value, this capital sigma will never change. It's just based on the data. Then we have our vector of unknown values, our weights that we want to solve for. Sometimes people will call these W's for weights, but they're traditionally called lambda. Just the weights in our Kriging equations, again, like we have here. And then we have our covariances between each data point, 1, 2, and 3, and the unknown estimate location, so the new point that we want to estimate. So the covariance between point 1 and our new estimate location, the covariance between point 2 and our new location, and the covariance between point 3 and our new location. So 0, x naught, and sigma naught, those are going to refer to our estimate, the location where we want to make an estimate. And so then what this is going to give us, now hold on a second here, what do we know, what do we don't know? So we know capital sigma, we know all these covariances. How do we know what those are? That's based on our variogram analysis. So we can do variogram analysis, we come up with a variogram model with a sill, range, and nugget. Maybe it's a Gaussian model, maybe it's an exponential model. And we can use that model to populate these covariances. So a variogram model, it gives us the covariance as a function of distance between points and direction. We can use that model to calculate what these covariances are, just given the data locations themselves. So these covariances don't depend on the data, they only depend on the location of the data. Same thing here with these covariances, the covariance sigma 1 naught, sigma 2 naught, and sigma 3 naught. These don't depend on our data, they just depend on the distance between each one of our data points and our new location where we want to estimate data. So all the sigmas that you see here, we can calculate using our variogram model, And we have to decide what that is. That's part of the process, the estimation process. We have to decide what variogram model we want to use, and that's based on our variogram analysis. And then from that, we can calculate what each one of these sigmas are, fill up these matrices and vectors, and then what we don't know is the lambdas. We want to solve for the lambdas, and we can set this up as a matrix vector system like is shown here, and then solve this system for this lambda vector. So if we were to do this in Python, for example, we would create our matrix of sigma ij's, we'd create our matrix of sigma i naughts, sorry, our vector of sigma i naughts, and then we would put those into a least squares solver like Python's numpy.linalg.lstsq. We could put that matrix and that vector into that solver and solve for what these lambdas would be. Same thing with Google Sheets or Excel. You can set up these matrices and vector, or matrix and vector in Excel, and then use the linest equation in Excel or Google Sheets to solve for what these lambdas should be. Just a linear system of equations that we're going to solve. So there's really 3 steps here that we've had to go through. Number 1, we had to do our variogram analysis so we could get that variogram model. Number 2, we had to populate this whole linear matrix vector system so that we could solve for these lambdas. And then finally, after all this work, we get our lambdas, we plug them into this expression. So these lambdas are going to be the weights that apply to each data, and we just multiply each of the weights by that corresponding data point, sum them up, and that is our weighted average. That's our estimate for z at our new location x0. Okay, so that's the process that we walk through when we're doing Kriging. Now, this is, of course, the simple Kriging equation, so we've assumed that the average is 0. We can also look at the uncertainty. We can get the uncertainty, and I derive what the uncertainty is in a different video. I'm not going to go through that here, but this is our estimation variance for our simple Kriging system here. So let's see here how to calculate or determine the sigmas. I sort of already talked about that. That's our variogram analysis, but this is just to make it explicit here. And then once we have our model, we find the parameters, we fit the parameters of the model to this empirical variogram, and then we can simply take this expression now for the covariance, whether we're using an exponential model or a Gaussian model or a spherical model, any other type of model, we'll know what the covariance is as a function of h. And we simply take our distances between each pair of our data points. Actually, let me back up here. So for each pair of our data points, we know what the distance is between them. We plug that into our covariance. That gives us our capital sigma ij here. We know what the distance is between each of our data points and our new estimated location. We plug that into sigma I naught here. Sorry, we take those distances, plug them into our equation, our covariance equation here, and that's what we use to populate then this sigma I naught term, sigma 1 naught, sigma 2 naught, all the way up to as many data points as we have. And then we can solve that system for lambda.